What we are going to learn in the second half of the class is magnetism and the relation between electricity and magnetism. So for the first half, what we learned were like mathematics first, like basic math, plus electrostatics. And as I said, electrostatics is the situation where charges are stationary, charges doesn't move, right? And today, and probably next couple of weeks, what we are gonna learn is the situation is called magnetostatics. Magnetostatics means we have current, but the current amount doesn't change as a function of time, okay? So charges are definitely moving in this case because we have current, but this current, the time derivative of charge movement is constant as a function of time. Okay, so first, the how it is composed is very similar to the electrostatics. What we are gonna learn is first magnetostatics in free space, and then we are going to learn magnetostatics in materials, okay? And then we then start looking into electrodynamics, what is called electrodynamics. Electrodynamics means the dynamics term means things are moving around or things are changing as a function of time. So once we learn about magnetostatics, we're gonna deal with the situation that the current changes as a function of time. Then electric field and magnetic field are no longer independent, but they are just connected. And then you're gonna learn how to deal with that type of situation. So as a first step, let's learn about magnetostatics. So everyone knows about this stationary force, like electrostatic force at the moment, right? F equals QE. This is just a force due to a stationary charge. And then you probably also learned in your high school physics that you have a Lorentz force. So Lorentz force is not only the electric force, but also the magnetic force, right? When charge Q is moving with velocity U, then it feels the force when there is a magnetic field, and you can obtain the force amount and direction by taking the outer product or cross product of U and B, right? And this term, the second term, is called magnetic force, okay? And of course, magnetic force is always perpendicular to U, which is the movement of the charge. It actually doesn't do any work to that charge, right? Because it's, in order to do any work, you need a field component that is parallel to the direction of movement. But by definition, Fm is U cross B. So it's F is perpendicular to U. So this is 0. So there's no work associated with it. And then you can easily derive from this equation, like F equals Q U cross B. You can also obtain the force exerted on a current carrying loop. So what you need to do is you just change U as a function as dl dt, right? And then change the time derivative to like the charge amount, and you get like df is equal to I dl cross b. Okay, so when you have a current carrying wire, and if this is infinitesimal length component, then dl multiplied, dl cross b gives you the force that this current carrying wire feels. Okay, so when you obtain, if you want to obtain the force on a closed current loop, all you need to do is just take a closed loop integral. Okay, so this is just the basic introduction about the magnetic force. And then this is a bit too easy problem, but this exercise gives you this type of a situation. So you have a electric field in y direction, and then you have a magnetic field in z direction, and then you shoot a charged particle with a function with a velocity u. So what you want to do is this charge does not get deflected as it moves, right? So in order to do that, let's say if the charged particles charge amount was q, then due to the electric field, the charge wants to go this direction, right? Upward. And then if you take u cross b, u cross b, you realize that magnetic force is applied on opposite direction. So the question asks you how to balance between magnetic force and the electric force, right? So electric force amount is q e naught, and then magnetic force, of course, is u cross b, right? So in order to make it equal, it has to be the same. So then from this, you can easily obtain the amount of the B field. So this is the solution, E divided by U. So this is just a simple example, like why about the magnetic force, just to give you some refreshment. And what we are gonna learn from now on is the main topic. So you remember in our previous electrostatics, we learned two important laws. The first one was Coulomb's law, and second one was Gauss' law, right? So we are gonna deal with the counterparts of that laws. So the counterpart of the Coulomb's law is Biot-Savart law, like what is Biot and Savart, like these two guys developed this theorem. And then the counterpart of Gauss' law is Ampere's law, okay? So what we are gonna learn is we first learn, like as we did in electrostatics, we first learn like Biot-Savart law, and then we will deal with Ampere's law later. And of course, when in order to apply Ampere's law to the system, we need to deal with symmetry, right? So we are gonna revisit the symmetry argument here in this chapter. Okay, so first, Biot-Savart law. So these two people, I guess, supposed to be French. Not totally sure, but I wish I just guess these people are French. Correct me if I'm wrong. But anyway, these two figure out that B field created due to a current can be written like this. Okay, so mu naught 4 pi is just a coefficient, like 4 pi epsilon naught in the electrostatics. This is just a coefficient, and then we call mu naught as a vacuum permeability, which is defined like this. And then if you look at the equation here, of course the magnetic force, the magnetic field is proportional to the current amount, and then dl is how current flows, like a vector segment cross AR. So in this case, AR is the unit vector from the source position to the point of interest. And then R square, of course, is the distance between the position of interest and the source position. So if you look at the equation, it's pretty similar to Coulomb's law. So if you recall Coulomb's law looks like this: 4 pi epsilon naught, and then what was it? like Q divided by R squared, right? And then AR. So it's very similar to Coulomb's law. It's inversely proportional to the R squared. That's the same part. But the main difference is that it does not the electric field direction is not parallel to the vector AR, but it's perpendicular to AR. That's the main difference. And then it involves a cross product, and that's just one big difference between the electric field and magnetic field. Okay, so as we did earlier in Coulomb's law, we can of course think about many different forms. So line current is just the basic form of current, right? And in this case, you need to do line integral in order to obtain the B field. And you can also think of sheet current, right? And in this case, the current is flowing on a surface, right? And the thickness in this case is assumed to be negligible. Okay, so it's just, 2D sheet current. And this is just the 1D current. And then here you can also think of volume current. In that case, you basically think of a wire actually have a non-zero radius, so that the current flow can be obtained by integrating the surface, cross-sectional surface of the wire. So in all cases, the change of formula are just trivial, right? You just integrate line integral, and then it becomes a surface integral and volume integral. And then to do a surface integral, you define a current density. Okay, but this is a line current density, and this is a volume current density. I mean, surface current density and volume current density. J and K, different notations. Okay, so these are, I guess these are all trivial for you. It's just definitions. So what we are gonna do today is try to apply Biot-Savart's law in actual system. So we will do a infinite line current first, and then circular current loop, and solenoid, and infinite sheet current. So we have like multiple examples. But the first one, I'm gonna do it with you together. So let's look at the Biot-Savart's law. Let me rewrite it. So B is what? Like B is mu0 4 pi line integration I dl cross AR R squared, right? So as always, what's important is to figuring out what's dl, what's AR, what's R, right? These are important. Writing these as a function of coordinate variables. So first of all, what's dl? Can anyone guess? Like based on what we did in our electrostatics, what would be dl in this case? dz. But dl is a vector, right? I mean, Ichung-Pil said it's dz, which is nice, but I think it requires some more elaboration. Like, could you, okay, right, az dz, right, that is correct. But I would like to say that, I mean, this is correct, but like based on our convention, I want to put prime here, right? Because like that was our convention, like put prime on source position. So this is my source position. So it has to be AZ DZ prime. Okay. Then what is R in this case? So we use a cylindrical coordinate in here. So what's R? Can anyone type in what's R? Here, this one, this absolute value of R, the distance. From here to here, right? Right, exact. Yeah, well, many of you actually got the correct answer. And yeah, but again, like I want to put prime for Z coordinate because it's source position. So it's like Z prime squared plus rho squared, right? And then AR is kind of trivial, like from here to this position. So it's like how can I write it? 1 over R. So it's combination of the Z component and rho component, a rho component, and then a rho component it's about rho, and the Z component is Z prime minus, right? So this is AR vector, DL, and R. So as we did in our previous Coulomb's law applications, this is it. Okay, now you plug these into the equations. You get this. So let me go through the equation a little bit. So plug everything in here. You get this, right? And then fortunately, AZ cross AZ gives you 0, right? It's just a cross product between two same direction is 0. So we only have AZ cross A rho. So AZ cross A rho give you phi direction, right? So you have only one phi component. And then if you look at the integration looks a little bit complicated. It involves like trigonometric substitution, like change of variable. Okay, but again, don't worry too much about change of variable. This is just a technique. So let's assume that you know how to solve this problem. Okay, just doing the change of variable, and you get the solution. Okay, from here to here, don't worry too much. It's just a mathematical technique that you don't need to memorize. And then once you calculate this, you get this answer. Mu 0 I divided by 2 pi rho. Okay, mu 0 I divided by 2 pi rho. Okay, now it reminds us like the case of infinite line charge and then the electric field associated with it. So if you remember the solution in this case, electric field was also proportional to 1 over rho instead of 1 over rho squared, right? So here the same. The solution is proportional to 1 over rho, right? Because the same dimensionality. And then also the solution proportional to I, and in this case, the solution proportional to the line charge density. But the direction here, in this case, it's a phi direction. It's just a rotating direction with respect to the z-axis. Whereas in this case, the direction is a rho, like it's just radiating direction. That's the big difference. But in terms of mathematics, they're basically the same, like in terms of just arithmetics. Okay, Kim Junmo asks, do we always choose the TL direction to be same as the current direction? Yes, that's by definition, yes. TL is actually the direction of current. That is correct. Okay, so any other question? Again, I wish our lecture, our class is interactive. So I promote you ask questions. And again, it's okay if even though your questions are not even relevant to the course contents. Okay, just please try to come up with any question and then do a practice. In my case, I was actually same as you, right? I did not. When I was an undergraduate at KAIST, like long time ago, I was as I said, I entered KAIST at 2003, and graduated at 2006, and then throughout my undergraduate period, I guess I didn't raise any question. Like I didn't raise but less than 10 questions, I guess, in total for these 3 years. So and that was fine. Actually, I had no problem learning things, because when I basically learned things from textbooks rather than lectures. So I prefer to read textbook all the time. So if the lecture doesn't check the attendance, I actually did not attend, and I just read textbook and try to learn it, and that worked pretty well, and that was very efficient, at least for me. I was usually taking very many classes than average, so it was more time efficient for me to read textbooks rather than taking classes. And there was no problems. And then after my undergraduate, I went to Caltech as a PhD course, and there also I have no problem taking courses, even easier. Like I guess the courses in KAIST was a bit more challenging compared to the courses in Caltech. So and then, of course, I was really bad at English, but no problem, because I didn't took a lecture, right? My style is just reading books, no problem at all. And then I did really well in the courses, even when I was at Caltech. And I got like all the courses I got A+, like all the courses I took at Caltech. And then the problem actually happened after I finished my coursework. And after I finished coursework, I need to learn about the forefront of the knowledge, right? I have to do my research. And then the research topics typically doesn't have any textbook. I have to learn it through reading, say, research papers, but research papers are not well organized. In order to read papers, you need to read the references of the paper. And then if you read the reference papers, then there are many references. So it's really difficult to get a organized knowledge in that manner. So the best way to learn it is actually taking seminar from like researchers, and then ask questions to the researchers. And I was really bad at that, because I'm not accustomed to taking classes at that time. I could not like concentrate on a seminar like more than 5 minutes, right? I was defocused and then just get asleep, or like, it was a really challenging thing for me to get back to, to the mode that I can take actually lecture and then asking questions. So, I just recommend you to practice asking questions from now on. Okay, I mean, I understand that not all of you are ended up doing research in the end, but anyway, just asking question like is important in any field. Try to practice. Okay, too much side talk. Let's get back and yeah. So if you have like two current carrying wires parallel with each other, then how much of a force is going to apply between them? And now this problem becomes pretty easy because you can exactly calculate the B field due to one of the wire. So magnetic field at wire 2, so magnetic field at wire 2 due to the current I1, okay? So if you calculate this, you know that P12 is minus mu 0 I divided by 2 pi d. D is distance between these two. And then direction is going to be AX, I mean minus AX. So it's like, let me draw it. This direction, right? Because current I1 exerts magnetic field in this direction. So at this position, it's going to be minus AX, right? So you have B field amount. And then force exerted on this line segment is I2, TL2, P12, right? And there's a cross product. And because you know exactly what P12 is, and then TL is along, TL2 is along Z direction. So the force amount, the direction of the force is along Y direction. And then, I'm sorry, direction of the force is going to be negative Y direction. And amount is mu 0 I1, I2 divided by 2 pi d. Okay, so this is how you obtain the force between these two wires. And there's one question from Park Se-hoon. Yeah, so the question asks, can we assume that the force at each position of wire to be the same because the wire is infinitely long? Yes, that is true. Because wire is infinitely long, the force at each position must be same, right? This is the symmetry, due to the symmetry. Yes, and if Z is not infinite, then of course the force amount can depends on the Z coordinate. Okay, this is a nice question, and thank you for asking. Okay, so let's move on to the second question. Second exercise. Biot-Savart law for a circular current loop. So here again, we do a practice. We do a practice for to find DL again, AR, and R. So what's DL in this case? Can anyone type in DL in this case? Anyone? Yeah, rho, right. Rho D phi, A phi, and then I want to put here, and also here too, actually, right? Because this is the source position, right? And then Kang Yung said it's A phi, D phi, but you miss actually rho, right? Because this is a length component, you need a scale vector in this case. And what about R then? R is the distance between this position to here, right? The position of interest, 0, 0, H. And in this case, R is H squared plus rho prime squared, which is constant. This is constant, right? It does not depend on source position. And what about AR? AR is from source position to the position of interest. So you can also obtain this 1 over R, and it's just a rho minus rho a rho plus H AZ, right? So all these things are just the same, like everywhere, but I'm just doing this with you just to give you some practice. So here you can see DL, R, B, DL, and AR are given like this. And then if you plug them in, then you see this. And then I didn't actually put prime, a rho prime here, but I think it's better to put a rho prime in this case. Anyway, now if you evaluate the cross product of A phi and AZ, that's A rho, and the cross product of A phi and A rho is minus AZ, so it becomes like this. And then one good thing about this is that we don't need to evaluate actually A rho component, because A rho component is just the radial part, right? And then we know that the system has azimuthal symmetry. So there cannot be any preferred direction, right? There shouldn't be any preferred direction in this case. So this term must be 0 if you finish the integration. So this one is ignored, and you have only AZ component. And then AZ component here is very easy to evaluate. There's nothing is dependent on phi, so you can take everything out, and 0 to 2 pi d phi becomes just 2 pi. So just put 2 pi out, and you get this relation. Okay, I guess it's easy enough. So any question about this exercise? Just want to ask, how many of you feel this is a bit too easy? What I'm doing right now is a bit too simple, like too easy. So I'd rather accelerate the speed of lecture. How many of you feel it's a bit too easy? None of you? Oh, okay. Okay, I thought that I was a little bit worried about this is a bit too easy, because I'm kind of repeating the same thing over and over. So I just worried about like make you got bored. But it's not the case. Okay. Okay, well, that's good then. Okay, so this is how a circular loop creates the magnetic field. And then you can take this solution, so the magnetic field is along this direction, to solve solenoid in the next problem. So next problem is about the solenoid, the famous example. So you have current carrying loop and has many turns. And then here we define the number of turns per unit length to be n. Okay, number of turns per unit length. So let's say you take infinitesimal length dz prime, then the number of turns included in this line segment must be n dz prime, right? Because this is number of turns per length, and then you multiply length, then you get the number of turns, right? Within that line segment. So how this is related with the previous problem? So if somebody asks you to evaluate magnetic field at this point, right? Then what you need to do is basically want to solve current carrying loops, magnetic field due to a current carrying loops, and then add them up, right? From negative infinity to positive infinity. So, and then magnetic field due to a current carrying loop was obtained here. So let's use it. So this is the magnetic field due to a current carrying loop with dz thickness. Okay, so look at this part. This part is exactly from the previous solution. And then what we are doing is we multiply n dz prime. N dz prime is the number of turns, how many loops you have within that dz. So you just multiply it, you get the amount of B field associated with that line segment. And then what you need to do is to integrate this z prime from minus infinity to infinity, right? To take into account everything. And if you do that, negative infinity to positive infinity, you obtain like extremely simple solution, mu 0 ni. Okay, mu 0 ni along the z direction. And here in the final integration, there was a trigonometric change of variable applied. And as I always said, you can just, this is not an important part. Okay, so any question? So what we are doing is, okay, good. There are many questions here. Yi Chung-pil asks, okay, so if you think about the solenoid carefully, solenoid is actually having a magnetic wire with non-zero thickness. So strictly speaking, the beginning of a wire and after one turn, the end of the wire is not at the same position. It's a little bit slightly off, right? And it's going like on and on and on. So how can we assume this as a multiple loop? But like, this is very true, but think about this, like, so you perform the integration. What you need to solve is actually Ampere's law. I'm sorry, Biot-Savart law. And then the integration just looks like this. I dl prime cross AR r squared. And then, you know, this infinitesimal change in position wouldn't affect the result of the solution much, right? And that's why we can just ignore it. And especially when you are thinking about like an infinite solenoid, it's gonna learn like, you know, doing this forever. So there is another, there's a previous one running here. So on average, there's no problem just integrating multiple loop, right? Even though each loop are a little bit off in terms of starting point and end point, but like overall, if you think about the current density, they are actually the same, right? So there's no problem doing that. But that was a nice question. And then Park Chejin asks, unlike a loop, the ends are okay, but the same, right? Yeah, so Park Chejin asks the same question. Unlike a loop, the ends are misaligned. How can you approximate it with a loop? The solution, the answer is that it's basically infinitesimally different. So it's fine. So if you want to know whether you can make this type of an approximation or not, you need to solve, you first need to look at this equation first. If you look at this equation, and then if you find any region that the misalignment makes a big difference somehow, then you shouldn't do it. But here, this integration is very, how can I say, insensitive about a small change. And especially if you have a multiple turns infinitely, then in terms of a current density, it's basically the same. So that's how we can make this type of approximation. These are both of these are nice questions. Okay, so here we have a final example of Biot-Savart law. So the question is to find magnetic field at P position 0, 0, Z due to an infinite sheet of current. So here the current is flowing in this direction, AY, and the current density is K. And here we also just try to do ds, AR, and R. Let's just do it. ds, so here it's better to choose XY coordinate rather than cylindrical coordinate. Why? Can anyone answer why here cylindrical coordinate is not appropriate? So if you recall infinite sheet charge, and if you want to evaluate the electric field above it, we took cylindrical coordinate, right? But here we choose Cartesian coordinate, and that's more appropriate. Why here we cannot use? Yes. As Park Chejin and Kim Junho pointed out, XYZ coordinate is preferred, or not just preferred, it's actually must choice, because the current flows on Y direction, right? So that there's no azimuthal symmetry of the system. So it's better to align coordinates to the specific directions like the problem have, which is AY and Z. So XYZ is more appropriate. So in this case, ds, of course, then it's like a dx prime, dy prime, right? Infinitesimal surface component. And then R is x prime squared, y prime squared, z squared. So x prime, y prime means these are source position. Z unprime means it's the point of interest, right? And then AR, you can do it. It's you know how to do it. So plug them in, plug everything in. B field expression is given like this. And then AY is the direction of the current. So AY cross AY is 0. And then AY cross AX becomes negative AZ. And then AY cross AZ becomes AX. Right? And from here to here, I just erase AZ component. Why? Why I did that? AZ component becomes 0. Why? Here you have AZ, and here you don't have AZ. Only AZ component can be B. Yes, so many people actually got the correct answer due to the function symmetry. Like if you look at this, so you can answer in many ways, but here if you look at the functional form, it's odd function, right? And so if you perform the x integration, I mean odd with respect to the x prime. So if you perform x integration, the AZ component goes away. So I just erase it like ahead of time, even before I took the x component integration. Okay, so that's what I did. And then you got this, only AX component. And this, if you look at this equation, it doesn't look easy to integrate, right? AX, dx, dy prime, square root of x prime squared, y prime squared, z squared. It's not easy, but there are standard technique in this case. In this case, you can make it into a cylindrical coordinate, turn this into cylindrical coordinate again, like this, making basically the change of variables. And then this integration becomes extremely simple, like dx prime, dy prime, and then integration region is negative infinity to positive infinity, becomes what? Like rho prime, d rho prime, d phi prime, 0 to infinity, 0 to 2 pi. These two integrations are same, right? So you do it. Then phi integration is just 2 pi. There's nothing dependent on phi, so it becomes 2 pi. And then rho integration is also easy because you have rho prime here, and then here rho prime squared. So it becomes easy. So if you perform the integration, you get the solution, and this is the solution. So what it tells is that actually the magnetic field direction is along x when g is positive, and negative x when g is negative. Okay, which kind of makes sense because you have a current here. So by right-hand rule, if your magnetic field is going to be this, rotate like this. And then if you have a bunch of current lines, so that above the surface, it's x direction. Below the surface, it's negative x direction. Right? And the amount is mu0 k divided by 2, which is very familiar term to you, right? This is similar to the case of infinite sheet current, right? I mean, infinite sheet, the charged sheet. In this case, the electric field amount was proportional to the surface charge density, and that was it, right? If you remember, this was the electric field amount. And here the same, magnetic field amount is not dependent on the coordinate variable, but only depends on the current density in this case. So dimensionality are basically the same, but the directions are different. Okay, so any questions so far? Anything? Okay, if there's nothing, I'd like to give you just one more thing and then stop. Oops, sorry. Yeah, so let me give you one more thing. So I'd like to talk about Ampere's law. So Ampere's law is written like this. This is basically the counterpart of Gauss' law in electrostatics. And what it tells is that if you perform a closed loop integration of the B field, it's same as the current enclosed by the loop. So here, here is an example. So if you have a B field and then taking the integration along a closed loop, this is exactly same as the amount of the current passing through it. Okay, passing through the surface. And the Ampere's law can be written like this or that. This is an integration form. This is a differential form. They're basically the same. And what I want to deliver today is just the first example of Ampere's law. So what we are gonna do is we're gonna do the exactly same thing what we've done before, like just a few tens of minutes ago, which is the current, a magnetic field due to an infinite line current. Okay, and what we know from Ampere's law was B dot dl is mu 0 I. Okay, and everyone knows how to solve this problem, right? We need to choose Amperian path like this as a circle with a center at the origin, and then we can apply the Ampere's law. But again, like before we do this, we need to first determine the direction of the B field beforehand, because even though we pick the Amperian path like this, then what? dl becomes what? Let's say this is A or rho, then dl becomes rho prime t phi prime, right? And then a phi. So if we take Amperian loop like this, then what we get is like only the phi component, because here's a dot product, only the phi component of the B field. So it doesn't tell us about the information about A, B, Z or B rho. So what we need to do is, again, as we've done in Gauss' law, we need to determine, like rule out the possibilities first, like B rho, B phi, B Z, and then what are possible and what are impossible. And then each of these, we can determine whether these functions can depend on rho, phi, Z coordinate variables. So let's first do this. What we want to claim is that at any position, only B phi is possible. And then B rho and B z are impossible by doing symmetry argument, even before solving the problem. And then here, in case of Ampere's like magnetic case, we know that current and B field are perpendicular, right? That's kind of we know from like the equation, like B, because B field is I a dl cross AR. So B field and the current direction are perpendicular. So, and then the current direction is along Z direction in this case. So B field cannot have Z component. That's for sure, right? B and current are perpendicular. And what about B rho? How can we rule out the B rho component? So let me draw the case. So here we have current. And then this is B phi component. This is B rho component. So what's wrong about having B rho component? Can anyone answer? We actually ask the same thing for electrostatics, right? And in that case, we concluded that only E rho component is possible and E phi is impossible. But what about in this case? How can we argue that B rho is impossible? Okay. Okay. Right. Park Se-hoon, if everyone reads Park Se-hoon's chat, this is actually correct. If the situation in flipped on XY planes, like if you flip the system on XY plane, then what happens is that B, the current direction is flipped, right? So current becomes, because current direction is flipped, B direction also need to be flipped, right? But even though you flip the system with respect to the XY plane, right? It's just to flip it, B rho stays the same, which is a problem, right? So that there's no B rho component allowed in the system. I hope everyone agrees upon this. And now we know that this system only can have B phi. And then B phi can depend on rho phi z. And then is it actually true? Can we rule out any dependence, any variable dependence here? Like B rho can depend on everything? What we want to argue is that B rho is actually a function, B phi is actually a function of rho only, and it cannot depend on phi or z. How can we argue that? In this case, again, it's easier to apply the symmetry argument. Yes, by symmetry. So z direction, the source is infinite. So we have translational symmetry. Like if we move the system along z direction by a certain amount, everything's the same. So it cannot depend on z. And then similarly, if we rotate the system with respect to the z-axis, everything's same. So like the system itself is the same. So it cannot depend on phi. So that b phi can only depend on rho. So again, if I summarize, b in general can be dependent on, can be written as b rho component that is dependent on b rho phi z, and b phi component rho phi z, and then b z component rho phi z. There are 9 possibilities in terms of a dependence. And then by doing symmetry argument, we reduce it into 1. Only b phi rho component is possible. B phi component that is dependent on rho is possible, and all the other cases are impossible. Okay, and then once we get to this point, if we apply the Ampere's law, then everything's simple, right? If you choose the Amperial path like this, we can easily obtain the rho dependence of b phi function, and that's the end. That's the end of the story, right? But again, as I always emphasize, this is important. This is not important. This is important, like the symmetry argument and reducing the problem from and rule out the possibilities. These are the real importance. Okay, so this is all I want to say today.